Video number 3. So again, if you watch other two videos, you're going to see very similar steps, similar themes, similar everything. I'm just trying to get you guys, make sure you guys can see how to do this and formalize it. So let's talk rhombus. So let's prove the 4 points to make a rhombus. So the very first thing we have to do is to write a nice statement of intent. So it's a 3-part thing. It's a very formal kind of thing. Basically, it identifies what we're being asked to prove, how we're going to prove it, and then how we're going to know that what we proved is right, what we're looking for, what we're identifying. And this is where the definition comes into play. So we know a rhombus is defined to be a quadrilateral, obviously 4 sides, that has all sides the same. So what we're going to probably do is use a distance formula. But anyway, let's get into the actual writing part of this. Now this statement is not just for fun. This statement also identifies to the grader, me namely, that you know what you're talking about. So if you mess up in the mechanical steps, this is your backup, that you actually knew what you were talking about. You just made some small mistakes, and those mistakes aren't huge because they're very fixable. Concepts, though, are very, very difficult to fix because they're incorrect thinking. Anyways, let's get to this. So, let's go to a pen. Okay, so to prove ABCD is a rhombus, I will show, and now the labeling part comes in here because now we don't have to be like this line, that line. We can actually identify the lines. I will show AB, CD, BC, and AD are congruent. And now here comes the part where I'm going to tell you how I'm going to do this by using the distance formula. If the lengths are the same, then the sides are congruent. Okay, so that's what I have to go about proving. Notice that all you did is basically name the definition that all the sides had to be congruent. I added how I'm going to do it using distance formula, so that's what the reader expects to see. And I also identified how I know I'm going to be right. So if I use a distance formula and show all the sides are the same, like same length, therefore they have to be congruent by the definition of congruency, and that's all there is to it. So now what I have to do is actually perform that calculation. And I'm not going to perform the calculation informally, like I'm not going to count squares or anything like that. Like I'm actually going to use the legit distance formula. So we'll probably need to write that in somewhere. Let's just remind the reader that what the distance formula is all about. So distance formula is defined to be x2 minus x1 squared plus y2 minus y1 squared. Remember, this just comes from the Pythagorean theorem. To be honest, I don't like this form of the distance formula. I actually prefer this one better. If you take x2 minus x1, you're just describing how far apart the x's are, delta x. And if you take y2 minus y1, you're just describing how far apart the y's are. That's delta y. That's the one I actually prefer to use because I can usually just kind of count in my head. So either way, though, whichever one you use, you have to show the calculations actually happening, which means we probably need some nicely labeled points. So just go ahead and run the distance formula. Just for convenience, I'm going to go ahead and write these points down right here. So A, B, C, D looks like A is 1, 2, 3, 1, 2, 3, 4. So this looks like A right here. So B looks like negative 1, 1. That's definitely B. C looks like negative 3, comma 2. So that's C. And D, yep, that's going to be D here. So we're going to use the distance formula. We have to run them. We have to do it one at a time. So let's go ahead and just start picking it up. So the first one we got to show is AB. So we'll stick that way over here. The distance formula is going to be the change in y over change in x. I'm sorry, excuse me. Change in x squared plus change in y squared. I'm going to use this version of it, so I'm just going to do some counting. So I'm going from A to B. So A, the x's start at negative 3 and at negative 1. That's going to be a difference of 2. Going from negative 3 to negative 1 is actually plus 2. So B, at the same time, goes from 4 to 1. That goes down 3. Either way, it's just a change of 3, so it's just going to be 3 squared. So to simplify this, I'll take 2 squared, which makes 4, 3 squared, that makes 9. that makes the distance square root of 13. So if I can get the other ones to be also square root of 13, I'd be in business. So let's check out the next one. So AB, CD is the next one. So let's do the same thing. I'm going to use the same version of the formula. If you guys want to do the plug-in points and calculate thing, is cool. I just want to do some counting here because I can look at C and D and know how far away those X's and Y's are. Because if the C starts at -3 ends at -5, it just lost two values. But I'm just going to write it 2 because I am just talking distances here. So of course that's 2 squared because of the Pythagorean theorem. D goes from -2 to 1. That gains +3, so that's 3 squared. Hey, look, those actually look exactly the same. That is going to be 4 plus 9, excuse me. 4 plus 9. And so distance here is square root of 13 as well. That makes me pretty hopeful. I mean, we have 2 out of the 4 things already the same distance. What's next? So AC, looks like BC is next. So distance again, changing y over changing. I'm changing y squared plus changing x squared. I'm sorry, I keep reciting the slope formula in my head. So BC. Okay, so B starts at -1, ends at -3. That drops 2 values, but since it's a distance, I'll just count it as a 2. BC. So it goes from 1 to -2. That's a change in 3, so it's +3 squared. Just like the other one, so we're looking at 4 plus 9, which will be the square root of 13. So that's a third one in a row. One more and we're good to go. I didn't intend to rhyme just there, but hey, we all sometimes do it. So AD, so last one. So A starts at -3, ends at -5. That drops 2 values. So the distance here is going to be 2 squared. D, A to D goes from 4 to 1. That's a change in 3. So look, that looks the same. That's going to be 4 plus 9. That's going to be square root of 13. All right, so because I had a nice statement of intent, I want to show all the distances are the same by the distance formula. I've done that. I'm done. I'm good to go. I can actually just go ahead and move right on. So they want us to do something else, which proves that diagonals are perpendicular. So we should probably start in the same place with a statement of intent. Let's write it right here. So how do I prove that things are perpendicular? Well, I can go here to my diagram and I can kind of just test it out. Do they even look perpendicular to me? Well, actually, yeah, they do. So it seems to me that what I actually have to do is evaluate some slopes. So if I can show that these slopes of these two lines have opposite reciprocal slopes of one another, I should be able to prove they're perpendicular. That's like the definition of perpendicular, isn't it? So let's go ahead and write a statement of intent. There you are. Let's get a sense of the two lines. Oh man, I'm all over the place. Hold on. Let's see, A, C, B, D. So AC. All right. All right. So to prove AC is perpendicular to DB, let's double check that. That doesn't sound right to me. ACBD, it is right. To prove that AC is perpendicular to DB, I will show that AC and BD have opposite reciprocal slopes. By finding their slopes. Okay, so we need some kind of formula to help us do this. And so here's a good time to get to remind ourselves that the slope formula is delta y over delta x, a rise over run. Another way to say that is just the change in y, so it's actually a subtraction problem over the change in x's. Okay, so now we have something to actually use, a nice true formula to use as a basis of our work. And so we have everything actually defined right up here anyway. So let's just do it. Let's find the slope of AC. Okay, so we're going to use the A and C coordinates. So I know delta y over delta x. So change in y over change in x for A to C goes from -2 to 4. And then on the bottom we have -3, subtract off a -3. Oh, this is going to be weird. -2 minus 4 is -6. Negative 3 plus 3, because two negatives make a positive, is actually going to be 0. And so we're going to say this is actually undefined. Now what that means is that it's a perfectly horizontal line. I'm sorry, vertical line. Okay, now that's a weird result, but that doesn't mean we're sunk. Let's go ahead and move on and find BD slope. Okay, so again, we're going to use the slope formula, change in y over change in x. Uh, let's see, for B to D, change in y, well, it goes from 1 to 1. So that's weird again, isn't it? So BD goes from 1 to 1. At the same time, it goes from negative 1 to negative 5. So we have negative 1 subtract off a negative 5. Well, wait a minute. 1 minus 1 is 0. Negative 1 plus 5 is actually 4. So the slope here is actually just 0, which means it's a horizontal line. We've actually proven this then, because if I take 0 over 4 and invert it, I get something over 0, which is a negative reciprocal in my mind. Also, we can note that this is a vertical line, this is a horizontal line, which again makes them actually opposite reciprocals. That's by definition. And so although it's not exactly as we predicted, we're actually still going to be okay here because I showed the slopes actually have opposite reciprocals, and so we're done. To kind of make it safe, we should probably add a little bit more writing here, because unlike our previous example where what we intended to show is actually what we showed, this showed us kind of a weird result. And so it's worth it to kind of take a second and tell the reader that this is okay, this is still actually in line with what I thought was going to happen. So vertical lines, they are perpendicular to horizontal lines by definition. So AC is perpendicular to BD. And so that's an important thing to write here because it just wasn't really what we expected at the time. And so since it was a little different than our statement of intent, we want to go back and just assure the reader this is still good. Okay, so this is the wrap up of Rhombus with this. This is number 3. So we just have a couple more to go. Looks like we're dealing with kite next. All right.